All right, it looks like we're ready to go. This is part 4 of the hypothesis testing lecture, so let's get started here. The learning objectives for this video are to integrate the information that we've had so far about conditional probability and the null alternative hypothesis together. So put those things together and understand how conditional probability works with the null and alternative hypothesis. And this requires us to separate the concepts of the reality of the hypotheses, which one's real, from what we actually do in our research, and including both separating it from our empirical results and separating it from the decision we make following our examination of our empirical results, because both of those things have to happen. So we need to remember conditional probability. The likelihood of event B happening a certain way if event A also happens a certain way. And this is the diagram we have. If event A turns out like one way, then event B might turn out like this or like that, and then you have these two possible outcomes. But if event A turns out the other way, then event B could turn out like this or like that. And one way of looking at things is you have these two outcomes, outcome 1 or outcome 2, and you could arrive there one of two ways, depending on how event A goes. So it's just a very slight twist. Instead of thinking of event A as an event, let's think of event A as a situation that might be true or false, or might be this way or that way. Let's say the situation is this way, or it is not. Situation A is true or false. Now this is going to be the hypotheses, specifically the null hypothesis, but it could be either one as far as you know so far. Like the null hypothesis is true or it's not true. That's situation A. This kind of conditional probability happens in a lot of situations. So here are some examples of some situations in which this null hypothesis might occur, or this kind of situation where conditional probability, the first condition is that a situation has to be a certain way. And if it's a certain way, then another event might happen a certain way. So this is the same thing that we're looking at up until now so far with conditional probability. All we're doing is redefining event A as like a situation that can be true or false. That's all. But it's important to note in these examples that the true situation A, whether situation A is this way or that, or whether it is true or whether it's not, we don't know this, and that's null hypothesis testing. We never know whether the hypotheses themselves are true or not. We have to make decisions kind of in ignorance in this cloud of uncertainty. So if situation A is true, and I've changed that blue diamond to be a situation here, and apparently I'm shifting around. Okay. If situation A is true, then situation A sets up two possible potential alternate universes, and they're mutually incompatible with each other. They're mutually exclusive, and yet only one of them can be real. Either situation A is true or it's not true. So if it's true, then we're in this universe, this world where situation A is true. If it's not true, then we're in this world where it's not true. And then event B either happens in the world where situation A is true, and then you have the possibilities of outcome 1 and outcome 2 with the probabilities of event being true or false. Or event B happens in the world where situation A is false, where it's not true. And then you have potentially different probabilities of event B happening or not happening. It's important to conceptualize that there are these two possibilities for situation A, and that sets up two different universes. Only one of them is true. The key is that we just don't know which one is true. But one of them is, and one of them is not. Sorry, the coughing is continuing here. So I found an interesting historical reference that works extremely nicely here. Blaise Pascal was this polymath who did pretty much everything, and a super smart guy, and he seems to have been really torn up by the concept of whether the Judeo-Christian God, which he lived in a Christian dominant nation, whether the Judeo-Christian God was really there or not, whether he existed or not. So if you see this quote, you see that he was looking around in nature. He's looking around at nature. Is nature wondrous or not? Like looking at the wonder of nature and trying to use that to decide whether God is there or not. Now, God is there or he's not there, right? So Blaise is left in this state of uncertainty. He wasn't sure whether the wonders of nature were due to the influence of the God that he maybe believed in or not. So that's hypothesis testing, pretty much in a nutshell. It's a beautiful example of the kinds of uncertainty we deal with in hypothesis testing. So we could take this example and force it a little bit and say that Blaise Pascal is thinking of this universe that works like this. Either God exists or he doesn't. And then if God does exist, then nature might be wondrous or not wondrous. And so and that's the part he sees, is that nature is wondrous. He doesn't see the part where God might or might not exist. And so if nature is wondrous, then it's because God wants it to be. If not, well, he doesn't want it to be. And that's confusing and weird, but he could have reasons. If nature is wondrous and God doesn't exist, then you could still have both of those things happening, but it's because of a different reason. Now it's because God doesn't exist. It's in a world in which God doesn't exist. So both of those probabilities can happen. This is a conditional probability situation. Whether God exists or not sets up a different set of possibilities that still end up in the same place. You end up with the same place where nature is wondrous or it's not, but it could happen in a world where God exists or where he doesn't exist. So this is sort of Blaise Pascal's confusion about the world, which apparently was never resolved, because these quotes that I'm reading about Pascal, they came from his notebooks published after his death, and he seems to have not figured this out. So he only saw one thing. He saw some empirical evidence. He saw, quote-unquote, nature, which is the outcome of event B. He saw that it was wondrous or it wasn't wondrous. So from his perspective, he had this flipped around thing going on. Possibility number one, if he saw that nature was wondrous, it could be wondrous for two reasons, either because God exists or because God doesn't exist, right? If he saw that that nature was not wondrous, again, two possibilities, either because God exists or because God doesn't exist. And he's telling us in his journals published after his death that he wasn't sure which one it was. He's looking around and he doesn't see enough evidence to fully 100% convince him one way or the other. And this is hypothesis testing. We will never have enough evidence to totally convince us one way or another of which hypothesis is true, and we will never know which hypothesis is true. So we only see the outcome of a research study. We see some data presented before us. Possibility number one, we're going to see that the data might seem most consistent with the alternative hypothesis. So if the alternative hypothesis is true, then great. That's exactly what we would expect. But if the null hypothesis is true, and therefore the alternative is false, because we construct them so that only one can be true at a time usually, then our results are what we call a false positive. We think we supported our theory, but we're wrong about that. We didn't support our theory at all. Now the other possibility is that we could see data that seem most consistent with the null hypothesis. If the null hypothesis is in fact true, is true, then that's exactly what we'd expect. There's nothing to explain here. But if the alternative hypothesis is true, then we have a false negative. Our theory is correct, but we can't see that from the study. Now, I hope you can see that these two possibilities, we won't know whether the hypotheses are true or not. Therefore, we'll make this decision, and we'll never know whether we are making this error, whether we've got this reasonable assumption exactly what it seems, or whether we're making an error, this false positive or this false negative. So this is what's going on here. We've got the null hypothesis being either false or true. If it's false, then the alternative hypothesis is true. And in both situations, we have the data either being consistent with the alternative hypothesis or the null. But we're never going to see that. We can make this decision rejecting the null hypothesis or retaining the null hypothesis. And no matter what we do, there are two possibilities for what it means. If we reject the null hypothesis, we might be up here rejecting a null hypothesis that is in fact false. We rejected a false hypothesis. That's great, because we saw that the data were most consistent with the alternative hypothesis, and we made a correct decision. On the other hand, we might be here. We saw that the data were most consistent with the alternative hypothesis, right? Same thing. And we rejected the null hypothesis and retained the alternative. But this would be wrong. So we don't know whether we're up here or up here. Or if we see that our data are most consistent with the null hypothesis and we reject the alternative, we could be here making a big mistake, because you don't want to reject the alternative hypothesis if the alternative hypothesis is true, right? You don't want to retain the null if the null is false. So we could be making an error if we do that. Or if we make the same decision, we could be making the correct decision. So we're never going to know what our decision really means in truth. Pascal didn't know whether there was a God. What he saw in nature, the empirical data, he couldn't make that 100% certain as an indicator of yes or no, there's a God. But he still had to make decisions. He had to live his life. He had to decide probably whether to go to church and things like that, whether he was going to be a reasonable guy according to the moral values that his religion was teaching. But we don't know whether the alternative or the null hypothesis is true. The data that we see could be the result of either one being true, and this is always going to be the case. We are never going to find a situation where it is completely 100% clear that one hypothesis is true and the other one is false. But we have to make a decision about the null hypothesis anyway. We decide that one of these hypotheses is most plausible in light of the data, but we don't know whether our decision is correct. That's just the way it's always going to be. Now, Pascal came up with this interesting kind of probability gambling type situation called Pascal's wager, which was his attempt of kind of resolving this, which is actually relevant to statistics as well. Here's another annoying little twist. When the data are not consistent with a hypothesis, we can make a fairly strong statement. We can say we reject the hypothesis. Now again, this isn't saying it's false. It's just saying, well, for now, it seems most reasonable not to have this as our explanation. We can reject. This hypothesis does not fit the data. And in science, it's easier to find disconfirmation of a hypothesis or a theory than it is to find confirmation. And so when we reject the null hypothesis, that's fine. We didn't disprove the hypothesis or the theory it came from. It means we reject the hypothesis as a plausible explanation right now, but it's fairly strong. We say we reject it for right now. We're pretty sure this is probably not what's going on. Now, we aren't sure because we could be making a mistake, but we can say we reject this. But when the data are consistent with a hypothesis, well, we have to say something weaker, because in science you can't know whether a theory or hypothesis is true. The logic doesn't work that way. So we can't say things like we accept this hypothesis or we prove this hypothesis or anything like that. We have to be a little more wishy-washy. We have to account for the fact that the data seem consistent with one of the hypotheses, like hypothesis X, but that doesn't mean that we should totally accept this hypothesis. So we don't even use the word accept. We say we fail to reject this hypothesis. Or you can say we retain this hypothesis, which is equivalent. So, because logically, we can't prove things true in science. Occasionally, with a lot of work or with an extremely well-designed study or something like that, you can disconfirm something or prove something almost certainly false. But we're almost never going to do that in the social sciences because we don't have enough data. We don't have a big enough sample to cover all the bases. But it's still much stronger to make a statement that this is not consistent with a hypothesis. The data are not consistent with a hypothesis. We can make a stronger statement about that hypothesis's truth value. But that statement is just we reject it as a plausible explanation right now. But we can't even be that strong when the data are consistent with the hypothesis. All we can say is we're not rejecting it at this moment. So it's kind of annoying, and yet final annoying thing, when we do hypothesis testing, we're only going to test one hypothesis. Can you guess which one? It's annoying because it's the null hypothesis. We're never going to test the alternative hypothesis, which is, it's struck an awful lot of people. A lot of statisticians, a lot of methodologists have written for about a century now that this is a terrible system because we don't test the hypothesis we're actually interested in. So therefore, our decision is only about the null hypothesis, and that's why we can't make strong statements about the alternative, because we didn't test it. We didn't say anything about it. We can reject the null hypothesis or fail to reject the null hypothesis, but that's all we can say. Now from there, we will, as a matter of habit, go on then to say we find support for the alternative, or we retain the alternative or something like that. But the logic underlying that is not as strong as it could be because we only tested that null hypothesis. Now there are good reasons for that, but a lot of people have pointed out the problems with it. This is how we do things. Now we're going to try and counteract that in one way this semester by learning how to do confidence intervals, how to calculate confidence intervals. That's the 48% plus or minus 2% type thing. That confidence interval is the plus or minus 2%. And that's a method of trying to say at least something about what's actually going on in the data rather than just about the null hypothesis, which we don't think is true anyway. So the logic of this is a little weird underlying it, and yet it has a lot of benefits, this testing situation. That's the end of the first day of talking about hypothesis testing. Now, the next 4 videos will be talking about hypothesis testing for the second day.